Hi, everyone. Today, I'm going to share with you some our exciting results about the magneto effects on the formation of lunar surface water. As we know, solar wind implantation is a major source of water on the lunar surface. When I say water here, it means either OH or H2O or both. And also previous studies suggest that the formation process of lunar surface water can be instantaneous. And if that's the case, that means the abundance of surface water formed by solar wind will change with the solar wind flux. And as we know, in each lunar day, the moon goes into Earth's magnetotail. And when the moon is in the magnetotail, the solar wind flux can be significantly reduced. So here's a figure A, shows a schematic plot of the, I cannot use my point. So like the Earth Moon system and also the structure of the magnetotail. And figure B shows the animate measurements of a solar wind flux at the different lunar phases. What we see here is when the moon travels from solar wind into the magnetosheath, we see like a 50% increase of.
You should just be able to push and hold that top button and it should come up as a point at the screen.
Okay. Thank you. It works. Yeah. So the magnetosheath has like a 50% more solar wind and proton flux than the undisturbed solar wind. And when the moon goes into the magnetotail low, it's silent. So it's almost nothing. You can see the proton flux drops to almost like, less than 1% of the undisturbed solar wind. And it goes to another side of magnetosheath. You can see another 50% more proton flux. So, I mean, if the surface water formed instantaneously by solar wind, and do we expect to see the lunar surface water varies with the solar wind flux? That's what we're going to test in this study. And we're going to use MCube data. We will use all the data sets to get the best coverage. And also we're going to split it into 6 different field lunar phase periods. You can see labeled as here to bin the data. And because the synchronization of the rotational and orbital period of the moon, the effects of local time and the lunar phase overprint on each other. So we have to correct the local time to see the lunar phase effects. What we did is we used the trend on the lunar far side that's not affected by the magnetotail. We use the downward trend on the lunar far side to correct the lunar near side data. And okay, I want to point out is if there is no magnetotail effects, we will see a flat line after the correction. So here's the high latitude zone. Again, you can see it's almost flat. We don't see any like a strong variation. The deviation is from like a different regions because this is like 12 different regions stacked together to get the best coverage of the full lunar phase cycle. And for the mid latitude, we see very strong variations. We see a strong increase. Oh, no, it doesn't work. Yeah, anyway, you can see the dusk and dawn labeled here. You can see a very strong step increase. While in the center, the tail center labeled here, you don't see any strong variation. And for lower latitude, like an equatorial zone, you see similar trend, but the trend is smaller. It's like a very weak variation. Again, you can see the increase in the dusk and dawn magnetosheath. You see a relative flat line in the tail center. And even in the uncorrected data, we can see the trend. So here on your left hand, you can see the clusters of data in solar wind labeled there in the black dashed circle, and the clusters of data in the blue dashed circle in magnetosheath. You can see the downward trend, they deviated from each other, but they merged at the local noon. So this strongly suggests when the moon is in the magnetotail, you see in the magnetosheath, you can see a significant increase of water. And the special case on your right hand, the green circles, if there is no magnetic effects, you will see a downward trend followed by the dashed circle. But in reality, what we see here is like the region in the magnetosheath, you can see it's even stronger than the earlier morning data. Okay, so in summary, this is like the variation we see in the when the moon traverses through the magnetotail, we see a significant increase in the dusk and dawn magnetosheath. This corresponds well with the 50% higher proton flux. However, it's surprising to see a flat line in the central magnetotail because this is like a high temperature heating and also shut off the proton source. So that means you heat your sample and a high vacuum and a high temperature, but without any implantation, you do not see any water variation. So there must be something going on here because you don't lose it, it's a stasis. In theory, if you heat it, you will lose it. So there should be some replenishment of water during this time. So we propose two different possible mechanisms. First one is the possible water formation associated with the plasma sheet. Because when the moon traverses through the magnetotail, it spends over 40% of the time in the plasma sheet. And this is an example of electrons and ions flux measured by the Artemis mission. What we see here, the blue dashed line is ion flux. You can see the proton ion flux is very low. It's not enough for the water formation compared with the red dashed line. That's the black dashed line. That's a solar wind. However, another big difference what we observe here is electrons. You can see the electron flux has not been reduced much as the ions. And also electron energy is much higher than the solar wind. So we think there could be water formation processes associated with the electrons. I just list off several here. And we are planning to test this hypothesis using upload samples and the plasma environment similar to a plasma sheet to test this hypothesis. Alternatively, we think this can also be explained by the diffusion process. Okay, almost done. Because most of the data, more than half of the data were acquired during the local noon, as I circled in the red circles. So the top plot is equatorial region, the lower plot is the mid-latitude. The point is the moon may have diffused a lot of hydrogen in the earlier morning. The weakly bonded hydrogen can be diffused out faster at that time. When the moon approached the noon time, only heavy, strongly bonded hydrogen left. So the diffusion will be very hard. And then we see a constant steady state in the central magnetotail. And also we see slightly shift of the local minimum of water content past the local noon at 12. Okay, in conclusion, we do not see strong magneto effects at high latitude. This can be explained by the cold temperature. And we see a strong increase of water in the dusk and dawn magnetosheath in the low and mid latitude. This can be explained by the 50% increase of solar wind flux. And the water didn't show any strong variation in the central magnetotail and a high temperature heating and a shut off the proton source. We think either it's possibly there's some water formation processes with the plasma sheet, or is it due to the diffusion process? I explain it. And we will test this hypothesis in lab experiments. And one point here is like future continuous simultaneous observations of both water and solar wind flux are necessary because we can see I have to bin the data at 525 degrees, a very large lunar period to see the trend is discrete. So we need a continuous observation to get a full picture of how water varies in the magnetotail. And also it's important for understanding similar processes on other ALS bodies, not because they are in the plasma sheet as the moon, but because the solar energetic particle events, SEP events, may show similar effects as the plasma sheet because they all have high energetic electrons and ions. That's it. Thank you.
For maybe one question, anybody want to ask? Thank you.
Really neat stuff, Shuai. When you say water, though, is it OH and H2O, or is it one or the other? Is there any difference for what you're looking at and predicting whether it's H2O or OH?
I don't know, Carly, because you know the limitation of the MQ, right? So we only see
Yeah,
half
yeah,
of the
I
water
know,
bands.
yeah,
We cannot
yeah,
tell whether
yeah.
it's OH or H2O. But I think Brian or Tom, like, when they do the experiments and the modeling work, I think that they can help to explain whether it's mostly OH species or molecular.
Yeah, okay.
Yeah.